Alright, Ohm's law is going to be where we really work on current, and you are going to do Ohm's law to your little heart's content, or maybe. You're going to do it ad nauseum. You're going to know Ohm's law off the top of your head by the time we're done. Ohm's law basically tells us the relationship between the voltage and the resistance and how they affect the current. So our main way of showing Ohm's law is going to be V equals IR. Okay, so we need some definition of our terms here. V equals IR. So V is our voltage. Okay, and this is basically how hard the electrons are being pushed from one place to another. And it's related to your power source. Okay, so, you have a little D-cell battery, that's 1.5 volts. Okay, when we were launching our rockets, we had the little square battery, and that was 9 volts. Okay, or what we're going to use a lot in class are the lantern batteries, and the lantern batteries have a voltage of 6 volts. Okay, and so that's basically the push to go from the positive terminal of the battery to the negative terminal of the battery. And the electrons want to go from the positive into the negative. And right now they're separated. But when we connect them with a wire, this is bad, don't do it. Well, actually, we're going to do it when we do magnetism. But when you connect them with a wire, you give the electrons, now, this is our current. Our current's going to go from the positive to the negative. But our electrons actually go the opposite direction. So our electrons go from the negative to the positive. There's our electrons there. But our current, there's current. Our current goes from the positive to the negative. And we have Ben Franklin again to thank you for that, because Ben, 50-50 choice, poor guy. He's going to really have a complex by the time I'm done with him. But he had a 50-50 chance. He defined electricity as the flow of positive charge, because, he was a positive thinker. So it was a flow of positive charge, but now we know that the nucleus stays in place and it's actually the negative electrons that move. But that's how we define current. So it's the flow of positive charge. So it's the electrons going from one place to another. And that we're going to talk about some more, so let's leave that. And R is the resistance. It's your friction. It's basically how much you don't want to go from one side to the other. It's the friction in the wire. It slows down the current. So let's we've looked at voltage, let's look at current a little bit more. So our current is our flow of positive charge, and it's abbreviated with the Greek letter I. I have no idea why it's abbreviated with I. But it is basically the flow of positive charge, so it's how much charge flows per second. So it's kind of like the speed of the electrons going through. And it's coulombs per second, because we measure charge in coulombs, and time. Oh, this should be time down here at the bottom. Sorry about that. Charge per time, and remember, SI unit for time is seconds. We rename that the amp. Now, 1 amp of current is a huge amount of current. So a lot of times what we're going to be measuring are milliamps. Okay, so we have to remember what that prefix milli means. Do you remember? Milli means a millimeter. 10 to the minus 3, so there's 1,000 milliamps in 1 amp, or 1 milliamp equals 10 to the minus 3 amps. So you are going to have to convert your milliamps to amps. Now your current responds to the voltage. If you apply a bigger voltage, okay, if you get a bigger voltage, you are going to get a bigger current. And that kind of makes sense. If I'm pushing you harder, you're going to go faster. So if you have a bigger voltage, that's going to give you a bigger current. Current, Greek, we're going to remember abbreviate with I. Okay, bigger voltage, bigger current. That is part of Ohm's law. So resistance is a measure of how much a material slows down a current, and it's actually based on the design of the resistor. So if you're given a 10 ohm resistor, it's measured in ohms. We should know that. So it's measured, the unit is ohms, and we're not going to generally write ohms. We're going to have the Greek letter omega. That's the unit for it. So it'll be a 10 ohm resistor. That's how you'll see it. And once we have a 10 ohm resistor, it's 10 ohms no matter how much voltage you apply to it. But the resistance, if we have 1,000 ohm resistor, okay, which one of these sounds like it might slow down the current more? Yep. So if you have more resistance, you actually have a smaller current. That kind of makes sense. As you slow down the current more, then it's going to have less current. Okay, so how do we put all of this together in an equation? So Ohm's law comes out to V equals IR, whereas voltage and current are directly proportional to each other. And current and resistance, if you have the same voltage, if you're going to increase your current, then you're going to decrease your resistance, so that the product of these two, when you multiply them, comes out to the same voltage number. Okay? So our V, our volts, this is in volts. Abbreviated V, how about that? That's easy. Why can't all of our things be that easy? I is current, and that's measured in amps. And R is our resistance, measured in ohms. And most of the time we are given ohms. And a lot of our ohms are pretty big. We have 10 ohms, 1,000 ohms. Sometimes we have 240,000 ohms. So some things have really big resistances. One version of the equation, just as an aside that you might see, and it might confuse you a little bit, and you might be thinking, wait a minute, is that I equals V over R. Okay? That's, if you look at our given equation, V equals IR, this is the easier form to use. So this is the form we're going to use in class, V equals IR. This one shows the relationships. It shows these guys are directly proportional, and this is proportional. See how R is on the bottom to the inverse of R, so they're inversely proportional. And it's often one of the ways that they show Ohm's law. And also what it does show is that our current itself responds to the voltage and the resistance. Okay, so just like when we had force equals mass times acceleration, sometimes you would see that as acceleration equals force divided by mass. Acceleration responds to the changes in the mass and the changes in the force. You couldn't say I'm going to have 2 meters per second squared acceleration. You can't say I'm going to have 2 amps of current. Okay, the amps of the current depend on how big your voltage source is and how much resistance your material has. Okay, but these are less used. Okay, so we don't want to use that, especially since we have that R variable on the bottom. This is the most used. We want to use this form of the equation. All right, so that should get us started. And this one is a lot easier to solve than any others. We'll do some practice problems in class tomorrow.